In the last lecture, we thought about some general principles of sensory systems and how we create our sensory perception of the world. In this talk, I want to go into a little bit more detail about touch, cutaneous sensation. So in this first slide, we can see a cross-section of the skin, and one of the things that's obvious is that touch is created from the integration of feedback from a whole range of different receptors which respond to different aspects of mechanical stimuli. And some of these receptors are shown in this slide. For example, with hairy skin, nerve endings are wrapped around the base of the hairs in our skin and are very sensitive to light stroking that may not actually make contact with the skin surface, but bends the hairs, and that mechanical bending is detected by the nerve endings that are wrapped around the base of the hair. Within the layers of the skin are a whole range of different receptors, which have rather strange names from the people who first discovered them. So we have Pacinian corpuscles, which respond to vibration of the skin surface. The Merkel discs respond best to pressure, while the Ruffini endings respond to stretch. When we feel an object with our hands, if you've played the game of putting your hand into a black bag with different objects and trying to identify the shape and what the object is just by feel, you're bringing together all these different elements to create your sense of the object. For example, is the surface rough or smooth? Is the object heavy or light in our hands, and so on. And so our ability to do that depends on that integration of the different senses coming from those different receptors. But one of the important concepts to remember or to recall is that the nerve endings within those receptors are the same. What's important is the mechanical structure of the receptor itself, which acts as a filter to change the way in which the mechanical stimuli are detected. In this next slide, we're looking at acuity. We mentioned acuity in this last lecture, and this is an important feature of our sense of touch. One way of measuring acuity is through a test called two-point discrimination. And exactly as its name suggests, this is the ability to detect or differentiate between 2 points of contact on the skin. So if you imagine an experiment whereby you have two pins that are very lightly placed on the surface of the skin, when they're far apart, you can detect them as two separate pins. As they're gradually brought together, you reach a point where you can no longer detect them as two different or two spatially separate stimuli, and they feel just like a single stimulus. And so this is a measure of the acuity of your two-point discrimination of the skin. And what this slide shows is the variation in that acuity for different parts of the body. So if you look at the blue columns, you can see that the fingertips, there, the two-point discrimination is only 1 or 2 millimeters. The fingertips, as I'm sure you're aware, are probably the most sensitive part of your external skin, other than the tongue itself, which is also incredibly sensitive. Conversely, for the back of the shoulder or the calf, we can only distinguish between two stimuli if they're separated by more than 3 centimeters, which seems an amazing distance. So there is a really dramatic difference in acuity across different parts of the body. So why is that? Why do we have that difference? There are several determining factors, the most important of which are the density of receptors in the skin and the size of the receptive fields. I mentioned receptive fields in the previous lecture, and this is the area of, in this case, the skin over which that receptor is sensitive. In the case of your fingertips, there are over 2,000 sensory receptors per square centimetre of skin. And the receptive fields are very, very small, of the order of a millimetre or less. By contrast, there are far fewer sensory receptors in the area of the back, our legs, and their receptive fields are therefore much larger. And so this is an important feature of generating our two-point discrimination. Touch pathways are shown in the next slide. So we can see the path that a neuron will take from the finger up to our brain. The first order neuron, i.e. the one that comes in the periphery that makes contact with the receptor itself, runs from the skin, and in this diagram from the tip of the thumb, up the arm into the spinal cord, and continues on up to a region of the brain called the brainstem. So this can be a really long neuron. We've shown it in the hand, but if you imagine someone who's tall and the neuron is stretching from the big toe up to the brainstem, then that can be 1.5, 1.8 meters in length for a single neuron. In the brainstem, the afferent, the sensory fibre, synapses with a second order neuron that crosses over to the other side of the brain and travels up to a specialised region of the brain called the thalamus. And this region is often referred to as the gateway to the cortex, because almost all of our sensory systems relay through the thalamus in order to reach the cerebral cortex, the area of conscious sensation. From the thalamus, we have another neuron, the third order neuron, which clearly is going to be very short, that ascends to the cerebral cortex, where it terminates in a very specific region called the somatosensory cortex. And this region is laid out as a map of the body. So all the touchways from the hand terminate close to each other, and in a slightly different region, for example, to the sensory pathways from the forearm and from the upper arm. And this is the labelled line concept. So this next slide summarises the pathways, showing the three neurons that convey the information, the first, the second, and the third order neuron. And they also show the location of the somatosensory cortex in the brain. We've got a strange figure called the sensory homunculus, and this shows the incredibly distorted mapping of the body onto the somatosensory cortex. As you can see, the hands and face appear very, very large by comparison with the legs and the feet. If you think back to the slide about two-point discrimination, the face and the hands are the regions that have the highest sensory acuity because of the high density of receptors compared to the back and the legs. So the mapping onto the brain, the area of the brain that responds and is sensitive to those different regions, is a function of the density of the sensory receptors, and that in turn is a function of the sensory acuity that we have. Note that because the pathways cross over at the level of the brainstem, the left-hand side of the cortex receives information from the right-hand part of the body and vice versa. Now you might wonder, what's the significance of the synaptic connections? Why don't we just have a single pathway going up from the thumb all the way up to the sensory cortex? The synapses allow processing of the information at different levels. So the information is processed at the level of the brainstem, it's further processed in the thalamus, and finally in the somatosensory cortex. It allows connection with different pathways within the brain and within the spinal cord. And the synapses are also places where the sensory information can be modulated depending on what's happening elsewhere in the body. So we might decrease the significance of a specific sensory input, depending on what we're focusing on. So, related to that, you might ask the question, why aren't I aware of my clothing all the time? It's pressing on my skin, so why am I not aware of its sensation? And this brings us back to the point that I touched on in the first lecture, which is the sensory system is particularly interested, for want of a better term, in contrast and change. Maintained stimuli, so for example, the touch of my shirt against my skin. Once I've put my shirt on, there is rapid adaptation of the sensory system, and I only become aware of my shirt again, for example, when I move and it moves against the skin. So the sensory system is adapting to maintain stimuli and focusing, responding really strongly to changes in sensory stimulation.